reprise pendant...
Oui, parce que bon, moi, je ne maîtrise pas l'anglais, donc je préfère, donc j'aurai besoin de l'enregistrement. Donc,
on peut se parler après, si tu veux.
Ok, pas de souci.
Non,
Merci beaucoup.
En général, s'il vous plaît, je vous supplie, parce que rappelez-moi qu'il faut déclencher l'enregistrement. Alors, avec ça, je cède la parole à Fritz en anglais.
Okay. Okay, then I'm starting to share my screen. Okay, should be full screen now, right?
Yeah.
Nice. Okay, so as we just heard, first with this, so what I'm going to present you is mainly work I did in Milan over the 2 last years, because I was in Milan over the 2 last years, with these 3 people. So yes, it's going to be about concepts, and just for clarification from the beginning, in this talk I won't differentiate between concepts and word meaning. I'm going to treat them as the same thing, and I'm going to use the words interchangeably. I know that you can make arguments about this, but whenever you hear one in this talk, it's also going to mean the other.
Fritz, sorry, does your version of it show the 2? I have 2 bars appearing that are not wanted on the PowerPoint. Do other people see a horizontal and a vertical bar that shouldn't be there?
Yes.
Yes.
No, I don't. Is it also there when
horizontal bar.
Is it still there?
Yes.
Yes.
Yes, it moved.
Could it be your Zoom bar?
Maybe, yeah.
You mean?
I think this is your Zoom stuff.
So one is here
right now.
Oh, one went away.
This is what. Okay, and this is the other.
Minimize the Zoom stuff so that you don't see. Those are just different ways of.
Okay, this is.
No, it's better.
This is better, yes.
Yeah.
The second one is still there or not?
It is still there. It
Yes.
might block the titles on your slides once you maximize the slides again.
Okay, so this is, how do I minimize that? That's the upper thing with mute and stop video and these things.
Are you doing it with share part of screen or whole screen?
Part of screen. Should I just share the whole screen?
Try whole screen, maybe.
So this should be the whole screen.
They're still there, but it's a bit better.
Does this work?
That's all right. Oh, wait, no. Okay.
When you click on the file, it appears. It's like a selection on the file.
I can live with that. Actually, I can, yeah, I can live with too small spot as long as you read your title very clearly. I would suggest.
I want the title.
It stays small. the top bar stays small as long as you're not mousing over it. So just don't. Oh, that's better.
Yeah, that's better.
Like this? Okay, then I try it like this. So I have to click on it again. So I assume most of you kind of know what a horse is, and when you hear the word horse, you kind of get a meaning for that. And unless you assume a strong nativist view where concepts are innate, you probably agree that these concepts, or what a horse is, has to be somehow learned from. You have to somehow learn that from the experience you make with the world. And one part of this experience is language experience. So you might hear sentences or read sentences like, I saw a horse in the stable. Humans have been riding horses for millennia. How does a medieval knight handle his horse? Things like that. And from this input, you can make inferences about what a horse is. As an example, how this might work, when I give you these 2 sentences, on my way here, I saw a little wibby chirping in a tree. And they used to build these wibbies from white steel, but nowadays it's just aluminium. You probably haven't heard the word wibby before, but it has acquired some meaning from reading these sentences. So it's probably some little bird-like thing made from metal, manufactured. but you can learn about this concept really from this text. And what I've been dealing with the last years and what I've done some work to is models of how this learning from language can work. These are so-called distributional semantic models. And as we heard in the introduction, one very prominent distributional semantic model is latent semantic analysis. These models start from the assumption that similar things or words with similar meanings are used in linguistically similar contexts. So for example, in many occasions, wherever you can use nurse, you can also use the word doctor. So you might have sentences in your experience, which are the passionate nurse treats patients in the hospital, or a similar sentence with doctor. The nice thing about this idea that similar things occur in similar contexts is that you can easily formalize. There's some call happening.
Please turn off your.
Okay. So the nice thing about this is once you define what a context is, you can actually look at which words occur in similar contexts. So for example, when you define as a context the other words in the sentence, you can just count how often does nurse occur with patient, hospital, medicine, all the other words that you know. And you can do this for every word. And when you just take this example, you will see that the distribution of nurse over different contexts is very similar to the distribution of doctor over different contexts. And this is the reason why these things are called distributional semantic models, because they assume that the distribution of this word is informative for its meaning. And as you can see from these examples, there's a dog somewhere.
Excuse me, 1 second, Fritz. Un instant. Tout le monde, écoutez-moi.
C'est Aude qui a oublié
C'est
son
Aude Dufresne
micro.
qui son
Oui,
micro
c'est
est
Aude
ouvert.
Dufresne.
Je vois l'activité ici. Alors Aude, ferme ton micro s'il te plaît. On entend ton pitou.
Sinon, l'autre, il peut le faire. Hein. L'autre, il peut faire un mute.
Pour tout le monde, oui. Oui, mute pour tout le monde.
Okay, so we'll just continue. As you can see here, the distributions for nurse and doctor in this example are very similar, and their distributions are very dissimilar from the distribution of whale. So what you have here is when you take these rows of this matrix, you essentially have a distributional vector. And the distributional vector for nurse and doctor are similar, and they are dissimilar from whale. So you can compute a measure of semantic similarity, so how similar these things are in meaning, by just looking at how close the vectors are. And if they are very close together, their cosine similarity approaches 1, they are very similar. If they are not close together and their cosine similarity approaches 0, they are very dissimilar. And more recent models apply a slightly different technique. For example, this is like a small illustration of the word-to-vec model. In these models, you're no longer counting how often words co-occur together, but you're trying to predict one word from its context, so from its surrounding words, but it's still the same principle. In the end, you get a vector. The vector represents the distribution of the word over contexts, and this is supposed to be an approximation of its meaning. So you derive word distributions from large text corpora. The assumption here is that these text corpora approximate our language experience. So this is the language you actually hear or read during your lifetime. You have some learning algorithm on top of that, and this learning algorithm derives some form of representation, in this case, this vector format, from your language experience. So you start from what you hear, what you read, and from this you build some form of semantic representation. When you do that with large language corpora, you get something like this. So this is the word, I hope you can kind of read this. It's a bit small, but if you go close to your screen, you might read this. Similar words to mouse are several computer-related things like cursor and scrolling and pressing. Several small animals like hamster, rabbit, hedgehog, rodent, and lab-related things like DNA, gene, cloned, mutant. This is the semantic neighborhood of mouse according to one of these distributional models. And a nice thing about these distributional models is that they are actually able to predict human behavior in many different tasks like lexical priming or similarity judgments, categorization tasks, and so on. So this is promising to begin with, but of course, there are certain shortcomings. So when you take exactly this graph and make a Chinese version out of this, you suddenly don't understand anything anymore. At least I don't understand anything what's happening here. So there are some symbols and they are close to some other symbols, but this whole thing is completely meaningless to me because I don't understand a single one of these symbols. And since I don't understand a single one of these symbols, I also have no idea what these other things are supposed to be. And that's the symbol crowning problem as I understand it in a nutshell. So when you have no idea what anything means, this whole thing is meaningless. But, I mean, we don't just learn what a horse is from language. We don't just read these artificial things. We also make other experience with horses. So, for example, we might see horses. You might also make other sensorimotor experience with horses. You might ride on them. You might touch them. You might hear them, smell them, everything. In this talk, I'm going to focus exclusively on vision. This doesn't mean that I believe vision is the only source of sensorimotor information. It's just that it's kind of easy to handle at this point in time. And if you learn that this is a horse, you might somehow connect this with this to build a representation of what a horse is. There have been computational approaches to how to model this visual part of the representation of horse, for example. So how can you do this? One approach is collect ratings. So this is a very recent data set from Linnet and colleagues, which is huge, like 40,000 words. And for each of these 40,000 words, you have this profile of sensorimotor information. For example, a song loads very heavily on the auditory dimension, also on mouth, throat, and on head, but not at all on vision. On the other hand, something like lattice, where is it here, loads heavily on vision and not at all on auditory information. So this might be some form of sensorimotor representation of song, sensorimotor representation of lattice, and so on. Another approach, which you might be familiar with, are these typical feature norms. So you ask people, which features does a bear have? And they tell you it's big, it has fur, it is brown, it is black, it has claws, it has teeth. And you have some profile of perceptual features associated to that bear. What both of these things have in common is they also give you some form of vector representation. So by just making a list out of these values, you can have some vector representation of lattice and come to the conclusion that the vector representation of lattice, this sensorimotor representation, is not very similar to sadness, but maybe very similar to salad. And for example, bear is more similar to elephant than it is to song. I mean, this is nice. We can work with that. You can compute some form of perceptual similarity between these things. What I don't completely like about this approach is you have to ask participants about this. So it's something participants have to have this concept and then tell you about it. And this is something very different from what these distributional semantic models do, because these distributional models start from the experience. They have some learning algorithm on top of this experience and then tell you, okay, how does this experience shape the representation? Whereas when you collect ratings and stuff, you rely on participants already having this representation and telling you about it. And of course, you can have answer biases and so on and so on. One problem you always will run into is what happens when you suddenly want to have information about something that's not in your data set. So for example, if your sensorimotor data set contains 40,000 words, but it does not contain polar bear, you have to ask people about the polar bear. The network itself will never tell you this. And so what we were interested in is, can we have something that also starts from experience? How can we model how our visual experience results in some kind of vision-based representation of the thing? And I'm going to present you this now in this talk. What we are using is a recent class of computer vision models, so-called convolutional neural networks. In particular, we are using the VGGF model. And what these models do I'm trying to keep this on a very intuitive basis. Also because I don't really know what they are doing mathematically within this complete architecture. But what they are doing is you start with images and you train a network that tries to tell you what you see on this image. So you have a set of labeled images, annotated images, and the network is trained to generate the label from the image. The image is really just coded as the RGB code of each pixel. So for each pixel of this input, you have three values: the red color, the green color, and the blue color. These three values for each pixel of the image are the first layer of the network. And the last layer of the network is just a list of labels. Note that this does not necessarily mean that these vision-based models have anything to do with language. It's really just a classification. It just tells you this is the same thing and these are different things. What these labels are and what the semantic content of these labels is completely irrelevant for this type of network. The nice thing about this is once you have trained such a network, you can really input any image at the beginning and you will have some form of representation at the end. And we take as the visual representation of the image the second to last layer of the network, the seventh. This is a 4096 dimensional vector. And it's again a list of numbers. This has been done in previous studies, and what this second to last layer does is it captures kind of the Gestalt, like the rough visual arrangement of the whole thing. So what these networks supposedly do is capturing more and more complex visual arrangements. So the idea is that the first layers capture shapes like line orientations, simple, really very simple patterns and colors. And the deeper you go into the network, the closer you get to the actual classification. The groups are getting more and more complex, and the type of information encoded in these layers gets more and more complex. And we take as the visual representation for the image the second to last layer right before classification. do you have any questions so far?
Yes.
How does it get to
Yes.
words?
When do I get to words?
How does it get to words at the end? You said the last layer is words.
Yes, but it's really just, it makes a classification which is the same image and which is not the same image. So you always have in this last layer, essentially, it's a whole bunch of zeros and it's 1, 1. So when it, for example, when this is a picture of, let's say this is a cell, it's probably not a cell, but let's say this is a cell, then in the output layer during training, all the values would be 0 except where you have the word cell, this is 1.
There was another question.
Yes.
Yes.
Yes. You have been talking about concept in general. And
Yes.
as we know, concept is very large notion.
Yes.
So I wonder if the abstract concepts are considered in this approach.
Yes, I will talk about that at the end of this talk.
Okay, thank you.
Yeah.
There was another question.
Yeah. I do have a question. You at the beginning you said there is a difference between concept and word meaning. Just to understand it well, when we have one word, it can have different meanings. And
yes.
you're saying that we need visual experience to make the difference between different meaning about the one word. So the concept is different from the meaning. Am I right?
Mm-hmm.
Okay. Just to be sure that I understood it well. Thank you.
Yeah. I mean, in this talk, for me, concept and meaning is the same thing. But I know that you can have a very long discussion about the difference between concept and meaning. For simplicity, just assume for this kind of approach for now that every word has one meaning and refers to one concept. I know that this is not the case, and you can actually differentiate that within these models, but I think it's easier to follow when you just assume that.
So based on this presentation is that each word has only one meaning. You're not talking about one word with different meaning.
Yeah, I mean, you can see that these models are kind of able to differentiate different meanings, right? Because, for example, in a simple polysemous word like mouse, you can see that already a distributional semantic model can kind of get that there's some meaning aspect here which is different from the meaning aspect here. So you have a way of differentiating that within these models, but I think for now it's easier to leave that aside.
Okay, thank you.
I had a question as well, if possible.
Mm-hmm.
So can you go back to the Chinese version?
Yes.
So when you look in English, words are encapsulated ideas. So a complete word is a set of letters, and all of together those letters have a semantic content. However, in Chinese, that's not how it works, right? Because the pictograms don't necessarily represent concepts if they are added with other pictograms. Two pictograms, I'm sorry if that pictogram is not a word, but two pictograms together will not necessarily relate to the previous meaning of the first pictogram. It's not just a combination. So how does this model work with other languages that don't use like our alphabet and thus do not necessarily encapsulate one whole idea?
That's a very good question that I have to admit I don't have experience with. So I have only worked on English and German so far. So I mean, is there some form of compositionality with these symbols in Chinese or not? If there's some form of compositionality, I think these models should be able to handle that. And I will show you in the second experiment one way of getting there.
There is, I think, some extent of compositionality, although it may be, imperfect. In some cases, it's, a clear composition of the meanings of the individuals, and in others, it's like, maybe there was a logical sense in which it was composed 1,000 years ago, but now that's long been lost sight of, and who knows why it's made of those two, right?
Okay, but that's similar in English. I mean, when you have ladybird,
Yeah,
you have
it
the very
is.
same
It
case. Yeah, I'm going to talk about that actually. So if it's roughly compositional, then maybe the second part of the talk will.
But in any case, I thought that this, perhaps I misunderstood, but this model that we're looking at here on this slide and on the previous one with the English words, this isn't dependent on compositionality, is it? It's just a
No. This is just counting.
Association of symbols.
Yeah, it's whatever you define as a word gets counted.
Right.
Really, just like that. So you define what a token is, and then it counts tokens.
Right. Okay.
Yeah. Okay. Then I'm just going to continue. So so far I've talked about what the model does to individual images, but of course, your concept of horse does not depend on one individual image of a horse. You probably have seen different horses throughout your lifetime. So what we do to get to this kind of prototype representation, prototype visual representation, is we really just aggregate. So for example, to get to some prototype of what a pistol looks like, we just take individual images of pistols. They all have some kind of vector representation. Again, this is the second to last layer of the network. And we aggregate these individual vectors for different pistols to come to some prototypical pistol representation. And as you can see in this example, pistol looks very similar to drill, and drill does not look very similar to screwdriver. So the model will give you a high similarity between pistol and drill, and a low similarity between drill and screwdriver, even though on a semantic level, these are more similar because they are tools, and a pistol is, I mean, not really a tool, kind of. So now we have, at this point, we have one individual representation for each category, which is labeled with a word. And this is something that's similar to what we get from distributional semantic models, where we also have one vector per word. If you want to see some examples, what the model actually does. So in this column, you see the closest image to certain prototypes. So this is the closest orange image to the orange prototype. This is the prototypical wolf, and this is the prototypical sun for the model. And on the right-hand side, you can see the nearest neighbors to this. So orange looks very similar to lemon, pepper, grapefruit, tomato. Wolf looks very similar to fox, bobcat, wolfhound, lion, and so on. And on the left-hand side, you can see similar words to this word in a distributional model. And when we look at some rating data, so people had to say for pairs like potato, corn, either how much do they have to do with each other, or how similar do they look alike. You see some dissociation here in that our distributional model, the text-based model, is able to capture these linguistic similarity, these associative similarity ratings, and our visual model is able to capture how similar the things look alike, but not the other way around, which is some initial evidence that these models really capture some form of semantic representation of the thing and some form of visual representation or vision-based representation of the thing. And what we wanted to do now is to check, does this help us in explaining behavioral data? So you always have this idea that during word processing, you might automatically activate sensorimotor experience in order to understand the word, or as a byproduct, depending on your theoretical point of view. And we wanted to use this technique to show whether we actually routinely activate sensorimotor, in this case, visual experience in word processing. So we had a look at lexical priming. Yes?
Could you explain the previous plot in more detail?
This one?
Yeah, this one.
Okay, so it's a data set, and participants saw in this case, it's actually picture pairs. So for example, they saw a picture of a potato and a picture of corn. And then they had to answer one of two questions. One question was, how much do these things have to do with one another? The other question was how similar do these things look alike, or how much do they look alike? And so, for example, a pizza looks very similar to a coin, but it has nothing to do with a coin. On
so
the other hand,
high visual similarity and low linguistic similarity.
Exactly.
People would answer what they
Exactly.
thought.
Exactly.
Okay.
And on the other hand, when you take a coin and a banknote, they don't look similar, but they are highly related. They have a lot to do with each other. And what we find is that our semantic similarities, which we extracted from the distributional model, from the language-based model, they explain this how much do they have to do with one another part, like these ratings. And our visual model, which is trained on images and which uses these image prototypes, predicts these ratings, how similar do the things look alike.
I see. So the height of this bar here is sort of the correlation between
the height of this bar is really just
the answers people gave to that question.
Yeah, sorry, I didn't explain that. It's really just the t-value of
score.
the parameter in the regression model.
All right.
Yeah, so the regression weight in a way.
Thank you.
Yeah, sorry. Yeah. Okay, so we had a look at a visual priming paradigm. Not visual priming, a lexical priming paradigm. How does this look like? Essentially, people see two words in succession and have to say for the second word, either they have to pronounce it or they have to make a decision whether it exists or not. For example, when you get something like this, drill is a word, so you press yes. Xella is not a word, so you press no. Boat is a word, so you press yes. And what you usually find is that when words are similar, reaction times are faster. Classical priming effect. And based on the previous literature, the consensus seems to be that, okay, there is semantic associative priming, so you get priming effects for pairs like money and coin, but apparently, according to this literature, there are no perceptual priming effects. So even though a pizza looks similar to a coin, there's no priming between these pairs. But what these studies have usually done is, I mean, they're also a bit older now, like 20 years. You usually have this categorical design with kind of small item sets and very extreme items. So pizza and coin are in a categorical design strongly visually similar, but not associatively related at all. And then you have like 20 items or 30 items per condition. But with these models at hand, we can actually look at large priming data sets. So we took item pairs from the Semantic Priming Project Mega Study, which contains a lot of items, and for about 1,000 of them, we really had distributional vectors for both words and visual vectors for both words. And what we did is we looked at naming and lexical decision, so both paradigms within the Semantic Priming Project, at short and long SOAs. And for all these priming pairs, we computed...
Sorry, what's an SOA?
Sorry, stimulus onset asynchrony. So how much time passes between the onset of the first word and the onset of the second word.
Okay, thank you.
And for all these pairs, for example, pizza coin and pizza money, we computed the vision-based similarity and the language-based similarity. And what we find is that indeed in one of these conditions, that is in the lexical decision task, short SOA, we find a visual similarity priming effect on top of the linguistic similarity priming effect. So these are again the t-values of the parameters in the regression model. And this is even the case when we add this visual similarity after already having included the linguistic similarity. So it provides additional information about the size of these priming effects. So we find evidence that at least supports the assumption that there is some visual priming, which leads to the conclusion that we seem to activate this sensorimotor information or these vision-based representations early on in processing. The time course of these things is in line with current models of like the time course of sensorimotor activation. If you want to, I can discuss it later. I didn't want to include a long discussion of why we only find this in short SOA conditions. Do you have any questions on this?
Could I ask a little one about what you just said? You got it. I don't want. You don't want to talk about what short and long SOA. So can
I can talk about it. Yeah.
But is it that where is it more likely that that verbalizing the name of the image could play a role? In other words, you see it, and I would think that it would be long rather than short.
Yeah.
How short is short?
Like 200 milliseconds between prime onset and target onset.
And that's below the. And what's the latency for naming them?
You mean the average response time?
Yeah.
Yeah, it's quite short. It's about 400 or 500, something like that, after onset of the target.
So is your short shorter than that, and your long is longer than that?
Sorry again?
Is the short SOA shorter than the response time, and the long is longer than the response time?
No. Yes, it is shorter. Yes. Yes.
So you would, okay. So if you wanted to say that you're really showing an effect of the visual similarity on the word, on the word processing, then you would say we controlled for the fact that it's not really just a image word effect. It's really an image. You understand what I'm saying? Image, name of image, word. It's not image, name of image, word priming because it's too short.
You mean that it's not enough time to read the word and then activate the vision-based experience?
No, not to read the word. No, to name the image.
But there is no image naming. There's just word naming.
Oh, so I see. So they're not. Okay, sorry.
It's really just words. This task has no images.
Okay.
It's really just this thing here.
Okay, got it. Yeah. So there's no such artifact. Right.
Yeah. So the assumption is essentially that when you read the word, you get early sensorimotor access, you get early sensorimotor activation, and since this is not necessary to perform this task at hand, the sensorimotor information activation related to the prime can already fade before the target sets in at the long SOA. That would be our explanation for this difference here.
Got it. Thank you.
Yeah. But the crucial point is that there is no perceptual similarity priming. That's the point of this study. That this effect, essentially this pizza coin visual similarity priming, which is supposed not to exist according to earlier studies, does apparently exist when you consider large data sets with a graded similarity
measure. Let me say that for the Anglophones, because not know in French, not know in French is ne pas. What he's saying is that there is. Not that there's not.
Yeah, yes.
It's like it's hot kind, something like that. Yeah.
Okay, so essentially to get an idea of what this all means, this is best illustrated by this comic. I'm showing this comic because this comic is actually included in the paper for the study I'm going to present now. And it's actually a major inspiration for this. So it's not just some funny business, it really had some value in this research process. So essentially you say a word to someone, and what happens is it's not just some semantic network firing happening, but there's also the activation of visual experience with the thing. But what you can see here is, I mean, probably none of you has ever heard about or seen a giraffe pimp in his lifetime or her lifetime. I mean, you know what a giraffe is and you have visual information for that, and probably also with pimp, but the combination is new. And what this comic nicely illustrates is that even when you say something like this to someone, there's some visual representation activated during this word processing. So in the second study, we try to look at automatic grounded meaning combination, meaning when you hear a word combination, does it actually happen that you combine the visual information of these things into a new single visual representation? When you have a vector format of representation, meaning combination can be very easy. So the simplest possibility is you add up the vectors. If you want some representation for swordfish, you just need to add up sword and fish. So 1 is the sum of the first 2 dimensions, 3 is the sum of the second 2 dimensions, and so on and so on. Very simple combination model, a very powerful combination model. It has some minor shortcomings. For example, in such a model, swordfish would be exactly the same thing as fish sword, because addition is commutative. What's the English word for that? You can change the order.
Commutative.
Commutative. Okay. So we actually use some more sophisticated combination model, but I'm not bothering you with the details of this model. It's essentially trained on all existing compounds in a language and learns some weightings from these, and then applies these weightings to any new combination. You can really just think of this thing as some form of weighted vector addition, which allows you to have a different meaning for fish sword and swordfish. So it's an informed vector addition. But the crucial part that you need to know to understand this is the representation for swordfish is really just formed from combining, adding up in an informed way, sword and fish.
Sorry.
Yes?
The plus, it means concatenation of the vectors or addition?
No, element-wise addition. So the resulting vector has the same dimensionality as the constituent vectors. And it lives in the same semantic space and can be compared to all other words in the semantic space.
Okay, thank you.
You're welcome. I did quite some work of this with my colleague Marco Marelli on these like composition models, all on language. But of course, I mean, this is not bound to language models. You can easily do the very same thing for vision models. So when you have a vector representation representing a sword, like a visual vector representation for sword and a visual vector representation for fish, you can again just add up these vectors in an informed way to arrive at a vector representation for swordfish. So we can differentiate between language-based conceptual combination and vision-based conceptual combination. To show you what, yeah.
When you say that you can do this, I mean, of course you can do this, but will the vector that results from adding the sword and fish vectors tend to be similar from the vector you would get from just pushing through a picture of a swordfish?
I knew this. They tend to be quite similar. I mean, of course, they are trained to do that. So we never tried some leave one out method.
I see.
But I can give you some examples for words that it doesn't know. So these are some examples what the model thinks these words mean. all these words are not included in the training set of the model. So that we have in our image database, all these words do not exist. We have no image for an ice house. And this is what the model thinks an ice house looks like.
How do we arrive? Is that like an image that you put in?
Yeah, that's an existing image, and that's the closest image to the representation that we get. So we get some compositional vector representation for ice house. Of course, we have no image which has exactly this vector. So to illustrate this, we just take the closest image to that.
And are these images that the model saw during training, or?
No, because the training was performed on these visual prototypes.
Okay.
I'm pretty sure that these images are, no, I'm not sure if these images are included in the prototypes used for training, might be. But yeah, what I don't like about this is that it's not actually a new image, it's just recycled experience. At the very end, when I have time for that, I can show you a method of how to actually produce new images for that.
Thank you.
But this is just some, at this point, it's really just an illustration. What does it like when you ask the model which image that you know is most similar to an ice house, it will produce this.
Do you have an explanation on why Handbook is so much further off the mark than pretty much every other sample there?
I like Handbook. I like Handbook a lot because I think this pretty much looks like a handbook.
Cigarette carton or cigarette pack?
I mean, if you see that, could you tell that it's not?
Yeah.
Yeah, if you didn't know Winston was a brand of cigarettes.
Yeah, you're right, okay.
I mean, of course, I'm showing you the examples here that work very well. These are picked examples. There are examples which are way worse. But I think Handbook is quite reasonable.
In the previous slide, how do you come up with the weights?
The weights, so what you do is, it's a regression problem. So you have some compounds available in your data set. For example, when you have images of snowman and teapot and similar words, you can have this as the training objective. And then you just optimize these weights so that these existing combined images are best predicted from their constituent parts.
So it's the same weight used across all the combinations?
So what you do is, exactly. So what you do is, it's really one single set of weights for the first element and one single set of weights for the second element. And to arrive at these weights, you train them on all existing combinations. So for example, at the beginning, you could imagine they are all random. Then you say, okay, this is how snow and man work together in generating snowman. Then you have these blue things here filled out. And then you update these gray circles so that you predict this in the best possible way from this combination. And this you do over all compounds that you have, that you can observe.
Okay.
Since this involves matrices, it's a bit of a difficult thing, but assume you have the outcome 8, and the first element is 1 and the second element is 2. Then one possible way of getting 8 from 1 and 2 would be 5 times 1 plus 1.5 times 2 is 8.
But are you testing these weights across a test data set which is not used in training in the regression?
No. It's really what there is, there is. Yeah.
Okay.
Okay. So now that we have these combined concepts and vector representation for these combined concepts, what we can measure is how easy is it to actually combine this thing. So how much of ice is still pertained in the ice house and how much of house is still pertained in the ice house. In the language domain, this would be called semantic transparency. So for example, for swordfish, the transparency of sword is medium high, I would say, and the transparency of fish is very high. You have also compounds where this transparency is very low. For example, ladybird. Ladybird has nothing to do with lady, at least not synchronically, and nothing to do with bird. So this would be a very opaque compound. And what you find in the compound processing literature is usually that these things are processed faster the more related the parts are to the whole thing. So words like teapot are typically processed faster as compared to words like ladybird. And we can measure these similarities of the parts to the whole thing both in the language model and also in the vision model. So here we can measure the similarity between the visual swordfish, the visual sword, and the visual fish. Since these similarities are for some reason highly correlated, we averaged them for this study. And what we find is that in a large data set of compounds, so participants really saw single words written on their screen, like swordfish, ice house, and they had to perform a very simple task, like either read it aloud or press a button whether it exists or not, so a lexical decision, or they have to say whether it makes sense, this combination. So swordfish makes sense, but radio pen does not make sense. Participants saw these words and had to give their answers. And in these reaction times, across all these tasks, we find that compounds which are more related to their parts are processed faster. Which indicates that there seems to be, I mean, this was at least the hypothesis we started from, and the results are in line with this hypothesis. So this seems to indicate that in processing, we actually perform some vision-based meaning combination. And processing is faster, the easier it is to combine the visual information of these two things into one. And again, what we mean by vision-based meaning combination is really just this. You hear a combination and you automatically access the sensorimotor information and combine them. Any questions so far? Okay, how much time do I have left? Can you hear me?
Yes, I think it's 30 minutes if I'm correct, but I'm not sure.
Okay, that works. Okay.
I mean, it ends in 30 minutes, but if you want some more, you had good discussion while you were talking. If you want some, you have to make it a little bit less than that.
Yeah, I think I need about 10 minutes to finish.
Okay, cool.
Yeah. So what I've talked about so far is this lexical priming thing where I claimed that when you process single words, visual experience with these words gets activated, or the visual representations get activated. I talked about this conceptual combination thing, where I claimed that when you hear something or read something like giraffe pimp, you combine the vision-based representations for these things. But of course, you don't have vision-based representations for everything. So this only works when you have a vision-based representation for giraffe and you have a vision-based representation for pimp. What about stuff like this, abstract words? You have no visual experience with jealousy, because jealousy is a social construct. It's not actually a concrete thing that exists visually in the world. It has no clear referent in the visual world. And I mean, yes, this is the case for abstract words, but it's not restricted to abstract words. You have the same problem also for concrete words. So at the beginning of the talk, I introduced you to the WIBI. You learned about the WIBI, that it's this little bird-like thing, probably manufactured from metal. So this little metal bird. And I assume that you're not completely agnostic as to how this thing looks like. If I ask you to draw it, I think you would converge on something very similar. So it is a concrete concept, but you can make informed guesses about how it looks like. So you can connect this to visual experience. There's something happening in the chat. Does this relate to me or not? I will check this later. So how can you ground these thingies in perceptual experience? One possibility is the so-called acquired embodiment. That's the terminology from a study by Hoffman and colleagues, or Arthur Glenberg and I have called this indirect grounding in a recent study. You can use language as a bridge to sensorimotor experience. So you learn what a WIBI is from language, and based on other things. So in language, you now know that a WIBI is similar to a bird because it is used in a similar way as the word bird. You also know that WIBI is kind of similar to metal because it was used in the context of aluminium and white steel. So based on your language experience, you form some kind of language-based representation for the WIBI. And based on this language-based representation, because it's similar to certain things and similar to other things, you can make an informed guess of how it looks like. And in this study that I'm now going to present you, we checked whether language for non-experienced things actually contains the information that allows you to do that. So what we did is we took a set of 7,800 words for which we have both language-based distributional vectors and these vision-based vectors. And we trained a simple regression model on all these about 8,000 words that just tried to predict the individual dimensional values of the vision representation from the individual dimensional values of the language representation. And once we train this model, we can again insert any word on the left and get some representation on the right. And then we can look for the closest image to this representation, to this informed guess on the right. So for example, when we insert jealousy into this trained model, it produces as the closest image to the informed guess this picture.
So I'm still a little confused about how we're arriving at these closest images. Is the idea that we have some pre-existing corpus and we have vectors for each image in the corpus and it's just picking out the one that's the most? Okay.
Yes, exactly like this. So we have a large database of images. We have a vector for each of these images. And then we have some target vector, which in this case is the informed guess about how the model thinks the thing looks like. So by inserting jealousy, this has some dimensional values. This runs through the weights of the regression network. Then we arrive at some estimated visual representation for jealousy. There is no image actually corresponding to this visual vector. So of all the images that we have, which are like, in this case, I think 1 million or something, we just pick the closest to this vector. I see the
yeah. Sorry.
No.
What was the original label on the textual side for this image?
Siren. This image is siren.
Okay.
Yeah. I see the concerns with this method of selecting the closest image, and again, I'm trying to present a remedy at the end. So here are some examples. The closest image to the model prediction for stallion is this horse here. The closest image to the prediction for scout is this guy. Here's aspirin. And here's some abstract concepts: childhood, this one; jealousy, this one. I can tell you already at this point what the model does for abstract words is essentially producing pictures of humans. I mean, these look very nice. In most cases, it's really just a picture of a face of a person. And at this point, I'm still not sure whether that's a feature of the model or whether that's a bug of the model. I mean, you can make the argument, and I think it's reasonable to say abstract concepts only make sense as a social construct. There are no abstract concepts without humans. This might be one reason, but it could also really be a technical bug that it just produces humans. I'm not sure about this at this point of my research. What we did in the study is something very simple. We presented the model prediction to participants paired with a random image, so very, very weak baseline. And we asked participants which one is better described by the word. So they saw the word stallion on the screen, these two images, and just had to select the one that fits better. And what we find is that, first of all, there is a concreteness effect. So participants prefer the predicted image more, the more concrete a word is. But more importantly, we have above baseline, above chance level performance also for abstract words. So the performance of the model is on average always above 50% and significantly so. Which means that participants prefer the model prediction over a random image, which at least tells us that the model was able to pick up something, and something that participants agree with, which in turn means that we can make informed guesses of how something looks like just from what we learned in language. So we can use language as a bridge to indirectly ground new concepts in visual experience, because language provides the necessary information for that. Of course, one concern that you had here and that you had already for these combination models is I'm just using images that I already have. There's nothing new. Nothing is ever generated. And probably, I mean, if I had never seen a metal bird, this type of setup could not produce this image because it just recycles images it already knows. And if I have never seen this, then I can't think of it, and that makes no sense. So what we want is something that takes this estimated representation and produces some, based on this thing, some estimation of what this looks like. And we have started a project. We haven't tested anything yet, but I can show you how it looks like, where we use generative adversarial networks, which is essentially a model that produces images by essentially producing random patterns, random visual patterns, and then letting a discriminator decide whether it's a real image or not. And whenever you get a response here, you get a feedback into the model. This gets updated, and hopefully next time the predicted image is less easily identified. The generated image is hopefully less easily identified as a fake. And when you run that a lot, at some point these fake images should become indistinguishable from these actual images. And the discriminator cannot discriminate between them anymore. And at this point, training is done. Quick example, when we use this training set of clothes, so shirts, trousers, and so on, for the generative adversarial network, and then try to predict what a slipper looks like. As you can see here, slipper is not included in this training set, but it is related to boot, sandal, and sneaker, and we know this from our language-based model. It produces something like this. So because it knows that the language-based vector is similar to boot, sneaker, and so on, the image it produces is also similar to images of these things. And we would like to test this in the future. Okay, so that's mainly it. For the end, I've listed some possible discussion points, but I guess you have more. I think the first discussion point is something that I'm still not sure about, even though I published these things, but I'm still not completely convinced that they are really useful on a theoretical level, these things, or maybe it's just fancy tools and they look nice and impressive, but maybe they don't actually tell us something. I'm not sure. That's something we can discuss. Okay, so that was the presentation.
Okay, it's open for questions now.
Should I leave the slides on, or do you rather?
Take it off for a moment because it'll disinhibit people. People, please turn on your faces. Don't just show your names, show your faces. And let me kick it off with a question that I bet you Art Glenberg would ask you anyway, and has probably asked you. He's a co-author of yours anyway, and he's watching. What about the motor side of the story? I know you only do visual, so you don't do olfactory, you don't do auditive, but the motor side is really a different story.
Yes. I mean, I can imagine how to work with auditory stuff because you can encode audio files easily. I can imagine how this would work. Motor is difficult, I think. I mean, maybe motion capture could be one way to get there.
Art, what do you think? You have to turn on your speaker.
Yeah, did you ask me, Stephen? I wasn't.
Yes, you.
Yeah, I mean, yeah, motion capture I think is a way to get going, but what you're going to miss are the notion of affordances. You know, whether something fits in your hand or not, and yeah, whether you can actually make a particular sort of movement with your body. And so, yeah, I agree that that's a really good question and a good way to go. Personally, I have not been able to figure out how to do it.
No.
You know, because on the language side, I'm always trying to think, oh my God, how do I code affordances? How do I really get affordances into a formal model? And yeah, haven't been able to do it.
Yeah. What my colleagues in Italy have been starting doing is recording MEG stuff during language processing, like MEG patterns, but I mean, that's again similar to what you have in these sensorimotor ratings. That's essentially the outcome of the thing. It's not the affordance itself. It's a representation of the affordance that people already have.
Yeah. I think the problem is similar to what I was thinking in regard to your example of the giraffe pimp, in that it's no way that the images of pimp and giraffe are simply mushed together, right? Yeah. I mean, there's a lot of human knowledge, or perhaps affordances, you know, that had us put the scarf around the giraffe's neck, you know, that had us put the sunglasses on the giraffe's eyes rather than, you know, arbitrarily put the sunglasses. And so, yeah, I mean, I really admire the progress that you've made. But yeah, I see that there's still work to do. in terms of how we bring to bear our real embodiment, you know, not just sensory, not just motor, but how we, having the bodies that we have, can interact with the world.
Yeah. But related to this, where do we put the sunglasses example? I mean, the information is out there, right? You know that sunglasses are usually covering the eyes. So once you have identified where the eyes are, you can put the sunglasses there. And this is kind of what these generative models I presented at the end are able to do currently. So you can make descriptions of images, like there's a bird holding an umbrella, and they are getting close in actually producing this. So the information is available. Of course, that doesn't tell us that humans do the same thing, but the information is out there.
Good. Other questions?
I have
Yes,
a question
please.
about,
Sorry.
Yeah.
So I mean, there's a lot to be said with, the relationship between the question I'm about to ask and what we were just talking about in terms of how do you encode other modalities and other sort of modes of experience. But just limiting it to vision, in these cases where when we do this kind of retrieval, where we say like, okay, here's a compound word, what's the image in our corpus that's most like that compound word? It seemed like you were using that to kind of gauge the quality of the encoding model, or like its ability to infer these connections. But it strikes me that to the extent that this is you know, succeeding or failing, that might as much be due to the contents of your corpus as to the model itself. Like maybe the corpus just lacks an image that is an appropriate combination of those things. And if there were one in the corpus, the model would have no trouble finding it. So how do you disentangle that, or do you at all?
So for the, I think I have to answer that in two separate ways, because for the last study I showed you with the mapping thing, we try to do this with these generative things. So we try to generate pictures that have that adhere to or that fit a certain vector representation. For the combinations, we could do the same. So we could take the estimated combined vector and let something generate an image from that. I mean, you could also think about just drawing an infinite amount of random images and then calculating the vector for each of them and drawing the one that fits. That could also be. I mean, there's a finite amount of possible RGB images, right? You could do that, but it's not practical.
Yeah, it's finite, but in practical terms, infinite.
Yeah. So yeah, that would be one way to start actually generating this with the appropriate model infrastructure. But in the concrete study, I mean, this combination study involved no images. That was really word processing. So what we are assuming there is that that our combined vision-based representation kind of corresponds to some vision-based representation in the head, whatever that means. Does this answer your question?
Not exactly.
Yeah.
Okay, but let's go on. Est-ce qu'il y a des questions en français que je peux traduire? Vas-y. No.
Okay. The question isn't in French though, but it's just you talked about the images, and it seemed very clear that the images sort of sorted through a central element in relation to potentially contextual elements. And I was wondering how your model separates both central element from context, and if it does it take into account context to create a sort of visual semantic field that it also associates with other elements?
And that's something that we have discussed a lot while doing these studies. So you get both. You get when you have certain things that appear in similar surroundings. So for example, animals living in a savanna, they are usually surrounded by a similar environment. And the model learns that these things are similar also based on the context that you have in these images. So it does central element extraction, it does context encoding. But of course, these images are always labeled with one label. at least in the model that we used. It's not, there's a lion and there are also some zebras in the background and I think the current computer vision community can certainly manage these cases as well, but our model is really just, there's one thing on this image, and it learns from every visual cue it gets, essentially, from context and from shape and from color. And
Jean-Louis de Salle, est-ce que tu as un commentaire? Mets ton micro si tu as quelque chose, si tu es encore là.
Et voilà, bonjour à tous. Non, j'ai écouté, ça m'a beaucoup intéressé. Il y a pas mal de... Ah oui, I knew most of the stuff presented today, but I was quite interested in the confrontation with that, what people, judgment of people. And so, okay, many things to discuss, maybe not now. Okay.
You'll get another chance, Jean-Louis.
Yeah.
Other questions?
Yes. Oh, sorry. Who gets it? Guy? Okay. So I had a bit of a low-level question. So, well, first, thank you for the very nice talk. So I think you've, from what you explained, I get an idea technically of how you compute word similarity, and on the other hand, how you map picture to a vector representation of that picture. And then how you train that vector representation to predict a word. But then in the experiments, when you try to like predict back a picture, I'm sort of missed the part when you map a word back to a vector representation to a picture in the other direction.
Yeah.
And I would like to get a small idea, same order of details than you gave in the talk about that direction. And the reason I'm asking this is not just for the pleasure of knowing it, is because you've shown us like what happens when you try to get the closest picture in the training set of something, of a word that was not in the training set. And I'm thinking if I want to get like a small idea of what the model is actually doing in this case, and I'm finding I'm missing these parts of the mapping to just try.
Maybe I quickly put on the slides for that, because
maybe I just missed it. So sorry if I did.
No, don't worry. So it's essentially this. So for every word, we have a list of numbers. This is the language vector. And when we have a word available in the language space, and when we have a visual representation for the same word, for example, this is the visual representation for wolf, this is also encoded by a list of numbers. So you have two lists of numbers, one on the language side, one on the vision side for the very same thing.
Okay.
And then you can check whether these numbers are related to them, to these numbers, whether you can predict this side from this side. So for example, let's say wolf has the language-based vector 2, 1, and the vision-based vector 4, 2. And then let's say hound has the language-based vector 3, 1, and the vision-based vector 6, 2. Then all you need to do to get from the one side to the other side is multiply by 2. That would be the easiest case. In reality, every single dimension of the vision representation will more or less be informed by every single element of the language representation. And we just try to learn these weights from each dimension to each dimension with a simple regression model. Okay. So
which is
a multivariate, it's really just multivariate multiple regression, nothing else.
Okay, that's very clear. Thanks for clarifying this point for me.
Yeah, you're welcome.
Other questions?
Yeah, may I follow up on that for just a moment? And Fritz, can you go back to that that image?
Yes. This one?
Yeah, right. And so so we see the word for wolf and the image for wolf. But then do you do this, apply that regression? Is that regression, the parameters based on all combinations of words and images where there's an exact match?
Yes, exactly.
And then you use that regression model when you have a word that doesn't have a match.
Exactly.
Okay.
Exactly. That's completely what we did. And in this study, we actually did this on individual images and on the prototype image. It works for both.
Thank you.
Yeah.
There was another question there. Tufik?
Yeah.
Yes, thank you. First of all, thank you for the presentation.
Thank you.
I wonder, when you map language to the vision, how you do to deal with the lexical ambiguity. As
Not
you
at
know,
all.
a concept can be expressed using a lot of words. So when you label your pictures, I would say you may have a bag of words to label. Would you like to explain me?
Yeah. So in this study, really, we didn't care about it at all. We completely disregarded this fact. So we have each picture, we took one label for each picture. In the database, we actually have several labels per picture. So we can predict the same picture from different words. We can also do that. So for example, when you have this wolf, it could be tagged as mammal, animal, wolf. And then we can predict the very same visual vector from the word animal, the word mammal, the word wolf. That would also work. So I think if you really want to do this in a well-informed way, what you would need to do is take this picture database and really let people generate every possible word that describes what is on the thing. And then you could scale up the training thing. I mean, it's ultimately a question that's tied to not what the model does, but how the training data looks like. And we, at this point, just took the training data that we have and in the format that we have it. But of course, we can have more sophisticated, more detailed training data and probably should have to make this more robust.
Okay.
Now, officially, the time has run out. And therefore, without any conscience pangs, those who have to leave or want to leave can leave. But I'm going to leave the recording going on and continue the discussion until the last card falls, because I find it interesting. So go ahead, continue. And that includes Fritz, of course, if you collapse.
Yeah, no, it's fine.
Maybe one question. If you, would you say that maybe the semantics, there's really more semantics in the perceptual data set than in the word data set? And it's only because all our words are grounded in this perceptual data set that we use them always together, so that it is possible to build a word data set after that.
Yeah, that's a good point. So I think in the data that we have at this point, the perceptual side is very incomplete because it's static images of more or less individual things. So from this data as it is, you don't really learn a lot about which things usually occur together. So for example, a spider doesn't look at all like a web, but it's very similar and very related, and it often co-occurs. So in order to get to something like this,
a spider doesn't look like a web. It has a kind of central spoke structure.
Yeah, true. Oh, damn, bad example. A car doesn't look like a road.
Okay, yeah.
Yeah. So I think you would, to really get there, need more realistic training data. Probably movies are a way to start, maybe like this, and then you would see which things actually occur together, because this co-occurrence of things is something that's currently missing from the perceptual side, but it is included in the vision in the language side. And I think this is some data that currently the language model contains, but the vision model does not really contain. But I think that if you get to the complete data set, I think, yes, probably the perceptual side contains more or less everything except for made up scenarios. Where you talk about stuff that's not actually happening in the world. And I think this is something that language would still add on top of that.
Okay, but if we look at the learning process, I think that all the perceptual data set, or most of the perceptual data set, is built before any word data set can be built. In fact, the way I see it is that the parallel part that would be important to get to words is the development of the visual model. And by visual model, I go a bit further than color and form. I include in there movement, which is depicted visually. And anything that you can include in the visual model. And for the auditory model, words are in fact objects in the environment. And the auditory model has to first parse this sound environment and come to phonemes and words. And only when you have a certain database on both sides, visual and auditory, you can start associating words with images. And the images at the beginning come only as a whole image, and that has to be parsed the same way that we parse sounds to be able to get to words. And so in the development of all this, and I'm interested more in artificial intelligence than in linguistics. In the development of this, first you have to be able to build these two separate data sets for sounds and images, and after that you get to words, and only then you can start thinking about a word-based model, but that word-based model is fully grounded into the other two models. And I know that I'm using symbol grounding here, Etienne.
Okay, we have a question from Nikhil. Don't leave, Nikhil.
Can I quickly? So I completely agree. I completely agree that in development, the perceptual side comes first. I think, and that's why I'm always, that's an argument I've been making in this paper also with Art. Later on in life, our perceptual environment doesn't change that much anymore, usually on a daily basis. We don't really start seeing and making experience with new things. I think at a later point in life, once you have a certain base, conceptual space composed of vision and perceptual experience and language, we predominantly, I think, learn new things from language because someone tells us about them. So I think this language side is really important once you have a certain foundation that you can build on. Then you can start extrapolating from there and building new things without new experience.
But new words can be grounded into old words, which are grounded into.
Yeah, exactly. Okay. Exactly. Yes.
Yeah, Nikhil, go ahead. Nikhil, you raised your hand. Go ahead.
Je peux poser une question, s'il vous plaît?
Nikhil, you said you wanted to ask a question. Nikhil Kakodakar. He doesn't seem to be answering.
Sorry, internet is not is not stable. So yeah, so my question was more on the technical implementation side. The last slide you showed us with the network, the regression between the two embedding space.
Yeah.
My question is, why not train the convolutional neural networks directly with the embedding space of the text of the words instead of the labels?
Yeah, we could do that. That's really just because we had the two things and wanted to check if it works. So that's the most, we just wanted to see whether we can predict vision from language. And this was the easiest thing to do and to start with. This is definitely not the most sophisticated way to solve this problem. So I completely agree that having...
Sorry, I'm sorry, I missed you there.
Okay. So essentially, we did it this way because we had the things and just wanted to see whether we can predict vision from language. I completely agree that having one single pipeline that learns both simultaneously would be, I mean, a super sensible next step.
Okay.
Yeah.
Okay. More questions? Because otherwise I have...
I'm joining in from India, so my connection is...
Didn't hear you, Nikhil.
Je peux poser ma question?
Oui, vas-y.
Ok. Donc, je vais la poser en français.
Vas-y.
Ok, merci. Donc, bon, j'ai essayé de suivre un petit peu, vu que je ne maîtrise pas vraiment l'anglais. Donc, si j'ai bien compris, l'entraînement du réseau donc, se fait en 2 ou 3 temps. Donc, le premier entraînement, c'est l'étiquetage des mots, c'est-à-dire classer un ensemble de mots qui veut dire, par exemple, un ensemble de mots qui veut dire un seul, c'est-à-dire le nom d'un seul animal, par exemple, animal. Et puis, le même réseau, l'entraîner avec des images et l'étiqueter avec cet ensemble de mots, mais c'est avec les images. Et puis, après, dans le troisième temps, c'est la combinaison des mots pour dire l'étiqueter par rapport à la sémantique. C'est-à-dire...
Attends, il faut stopper là. So, is Geroud right to infer that what you described was that a network is first trained on the words, then treated on the images, and then they're integrated somehow in the same network?
No, at the moment we have two separate things. We have one purely language-based thing and one purely vision-based thing, and the two things are never actually integrated into one representation, which is definitely what one should do at some point, to integrate them in one representation. There's some work by Andrews and Villocco from like 2009 where they built like this conjoint vector space from language and feature ratings. I think something like this should be possible here, but we haven't done this yet.
Est-ce que tu as compris, Geroud?
Non, s'il vous plaît.
Non, que ce n'est pas le cas, c'est pas le même réseau. Il y a deux réseaux séparés, mais à un moment donné, ça devra être un seul réseau.
Ok, donc en deuxième temps, il prend les classes, les images et il va les classer, donc il va les étiqueter avec les classes de mots trouvées. Ok, donc par rapport à la sémantique, donc il donne donc dans la sémantique, donc est-ce que c'est un troisième réseau aussi pour la sémantique? Parce que pour la sémantique, on va donner des noms composés et on va donner leur sens. Donc le sens.
Is there going to be a third network that's a semantic one in which you give the word the combined words and their meanings?
If there's going to be one, or sorry, the question again.
Geroud, tu poses la question concernant un réseau qui n'existe pas encore. Tu demandes s'il y aura...
C'est-à-dire la sémantique n'existe pas encore dans le réseau. On ne connaît pas la sémantique. Donc le sens, c'est nous qui vont c'est-à-dire leur donner. Donc il y a les mots composés. Les mots composés, lui, il ne connaît pas leur nom. Handbag, donc la serveuse ou autre, donc en anglais. Donc, les mots composés, on doit lui donner donc en entrée un mot composé et à la fin, on va lui donner des classes, on va l'entraîner. Ce mot composé veut dire ceci. Donc, on va lui donner le sens. Donc, un troisième.
She's asking that when you're giving the composite combined words, are you going to do a separate supervised training to give it the meaning of those combined words?
Yes, there's one training process within the language-based things, and this is completely different from the training process within the vision-based things. These are two separate, completely separate things at the moment.
Donc, un autre réseau à part. Donc, vers la fin, donc pour le test, il donne une combinaison, donc image plus un mot. Donc, et là, c'est une autre combinaison pour le test, c'est ça.
Yeah, that's right. C'est correct.
Voilà. Donc là, on a un réseau donc entraîné pour une langue donnée en anglais, c'est-à-dire en anglais, on ne peut pas le tester, on peut pas l'appliquer pour une autre langue, le français ou le chinois. Donc les combinaisons des noms donc changent d'une langue à une autre. Donc,
Did you understand that? Okay.
That word combination works differently in French than in English?
And in general, whether your approach can be applied to all languages, including French and Chinese.
That's essentially an empirical question. So it works in German. It works very well in German, but German has the same compounding system as English. So, we try to do it in Italian, where you have head first stuff, like swordfish is not swordfish, but pesce spada, which is fish sword.
And it's inflected, so it's not just two words. It's really a word plus an inflected word.
So the most honest thing I can tell you is we haven't tried. The fact that it works with images is kind of promising because they don't really have like this modifier head structure that you have in language. I assume that it will work if you have a productive compounding system. So in Italian, it's kind of not really working, but you also don't really have compounds in Italian. I think it would work in French because in French, it's pretty systematic. You always have like rue de la de, right? You usually have this combination where you have the head, then some kind of preposition, and then you have the modifier. Right? So if you have a training set consisting of these things, and there is some common structure to them, the model, I think, would learn this and pick this up. Can I mute?
C'est odd.
Where's the sound coming from? I can't figure it out.
C'est odd toujours.
Okay, yeah. So essentially, if there is a systematic structure combining two things in a predictable way, then I'm very confident that the model can pick up this to make a job. But I don't have the empirical evidence.
Moi, je pense que en tant que combinaison de mots, ça se pourrait que ça ne sera pas évident, mais avec les images peut-être. Donc, une image peut dire le même sens. Ça peut être évident par rapport aux autres langages, par rapport à une scène d'image, mais par rapport à la combinaison des mots. Donc, chaque langue a sa propre combinaison de mots et le sens de la combinaison. Donc, ce n'est pas toujours le cas quand on combine un mot en anglais ou en français, ça donne pas toujours forcément le même sens.
Oui, but that's what Fritz said. Okay. It's an interesting question. Other questions? If there are no other questions, yeah, go ahead.
I do. So it's partly a comment, but I will ask a question. So at the end of your presentation, you asked whether or not this is actually going to give theoretical insights or if this is just a fancy tool. My question is about whether or not you could use predictions or you could generate predictions from your model and test them using neuroscience. And my inspiration basically comes from you were explaining how the convolutional neural networks work in terms of the visual processing. and it's very similar to how the brain processes visual information. And I'm wondering if you might be able to create a model that is more inspired from the neuroscience of how the human visual system processes this kind of information, and then from that generate predictions of your computational model and test them using some sort of neuroscientific.
But before Fritz answers, we're going to have a talk in this series on exactly this topic, Matthew.
Oh, okay.
But now you can
Nice.
answer.
Yes, so I mean, essentially these models are just applying the brute force of current computational power to a problem, which is image classification. They are not, I think they are not really informed by biological or neuroscience evidence. I think, I mean, once you know what's happening inside the neural system, you should be able to work to create a model that essentially simulates a brain processing an image, right? So in principle, this should be possible, which would be a very nice thing to have. And maybe it should even predict human data better than what we have here. What I was thinking at the beginning of your question, and please just stop me if I'm just derailing your question now, but there is a study from the 2000s where they show that essentially neural activation patterns during word processing can be predicted from these distributional vectors, that there is some structural similarity between distributional vectors and the activation pattern. It's a paper by Mitchell and colleagues, 2008. I'm not sure whether that's actually replicated or not. But this would be one prediction. So if that's really what the system does, perceiving an image and arriving at some form of representation, I mean, what happens in between in these different layers you should be able to find that somewhere in the brain with the right technique, if that's what happens in humans, or at least something that is predicted from these activation patterns. Because in the end, that's just what it is. I mean, these vectors are just activation patterns. And you can't check if that converges with what you have in actual neural processing or not.
I'm not familiar with that study, but I do know of studies that look at basically reverse correlation of they actually use movies and the activation in the brain and are able to predict one from the other. So I'm wondering if you might be able to take that as inspiration of finding the semantic content of those images and seeing if that, I guess, would be predictive of the products of your model, but that's very kind of down the road, I think.
Okay, Aude, mets ton micro, tu peux poser la question. Aude Dufresne, tu as posé une question.
Oui, je m'excuse, pas tout à l'heure. I will ask it in English, it's easier. I was just wondering if you have a lot of work for training your sets with the linguistic dimension, but for the visual, how many pictures do you use, and is it should be much bigger to get the real interesting semantic network. So I was wondering, how do you deal with that? And just to finish, is it possible to think of using words to search for images and enrich that base of images, which is used for learning?
Okay, the question is asked. Aude, now turn off your microphone because you have background sounds. Turn off your microphone. Okay, go ahead.
I might ask again for the second part of the question, but the first part of the question, so yes, the image data set, training set should be larger than the language data set, but it's not. So in reality, it's far smaller. So we have about, I think, 9,000 different words in our visual space. And these prototypes are generated from about 100 to 1,000 images per label, which is actually not a lot. It's quite small. The model is trained, the initial model is trained on about 1 million images from 1,000 categories. And this is available in the library, and we took this pre-trained model. So yes, I think in order for it to really make sense and really be an approximation of human visual experience, we would need a lot more data than what we have at the moment and what we are using.
Go ahead, Odd. Réplique.
Okay, so it's still a lot of pictures, but my second part of the question is, can we use the linguistic data set to search for images to enrich it? Because it could be, the idea is to have as many pictures that we can, and we should redo the training with a larger one if possible.
Yeah, I mean, the simplest way would be to Google all the words and collect the whole Google image search and use them as new training images. In principle, it's possible. At this point, it's really just a data management problem.
Okay, so it's just that the semantic dimension, the semantic virtual dimension might be, I mean, the semantic might be weak compared to the linguistic one that way. And it's very important to know, to have different, I mean, to have a real semantic, which is in fact visual semantic, a real one. I mean, so it would add the validity to it, but it's just a suggestion.
Yeah, yeah, I agree, completely agree. Like we are doing baby steps here.
Oh, I agree to being step by step.
Okay, please turn off your mic. That's it. Do you still have some energy, Fritz? Are you ready for 5 hard questions instead of easy ones like you've had so far?
Okay, yes.
First one, you said that what you mean by concept is meaning, but you didn't say what you mean by meaning.
I think the simplest, no. What do I mean by meaning?
Let me tell you what you don't mean by it. You don't mean the referent.
Yes, I don't mean the referent. That's for sure.
Okay, so now the rest is up to you. What do you mean?
I think it's definitely something, some form of mental representation. It's something in the head. It's something that a speaker of a language acquires and uses.
Well, that we knew, because we're all organisms who have brains, and there's something going on in our brains when we do whatever we do, whether we look at something, but that doesn't tell you what meaning is. We're trying to figure out what's in there.
Yeah. I can start from the operational level, I think, because the way I define meaning in these things is really some form of aggregated experience with a thing. So there is a certain, let's say, term, a certain term referring to an object, and the meaning in this sense is really just what we've learned about it.
So you don't mean an aggregate of experiences, you mean an aggregate of the effects of those experiences, right?
About how our system processes these experiences, yes.
What those experiences did to us. Well, yes, but we're waiting to see what kind of thing that is. So far, we know that we have words, we know that we see things, and we know that we've got the data that you described about what happens if you process these big data about images and words, and the correlations it gives you. But that still doesn't say what's going on in there. It's just telling that one of the effects of what's going on in the factory is the smoke from these LSA type distributional relationships.
Yeah. Yes. I think I'm not sure if I can give a more precise definition of what I mean by meaning with this kind of approach, rather than being an aggregate form of experiences.
Okay, let's move to the next one. It's a point of reflection. What's your answer to the, you almost, I think I know what it is because you almost said it, but what's your answer to the pet fish objection about combination of concepts?
I don't know the...
When you talked about the giraffe, but there's a long discussion in the literature about the fact that meaning cannot be compositional because whereas you can have you can combine the word pet and dog and everybody gets it, but when you say pet fish you get the kind of anomaly that you get with giraffe gigolo or giraffe pimp that you said before. So what actually is your answer to the fact that this is not just what you did with what we had with the giraffe with the scarf around its neck was just the kind of thing you would expect from the smoke coming out of the factory, which is that you send out some verbal smoke with certain correlations and some image smoke with certain correlations, and there's correlations between images and words, then you get a giraffe with something around its neck. But that's not what we mean by pet fish, and there is no such thing as a giraffe gigolo.
Isn't there? I mean, if you
could write of course, when you said that our limitation is that we are using the words and the images that have already appeared, and then we're trying, we haven't got the new combination. Well, those are all potential combinations. And the machine that is generating all those potential combinations is doing something. And presumably what it's doing has something to do with what meaning really means. But we're not hearing it. All we're hearing is all these associations between images and words and frequencies and co-occurrence and context. And because it correlates with some of the things we do, you're saying that's meaning.
So the point of the pet fish example is that a pet fish is a specific kind of fish, like a goldfish or something like that. And the model would not arrive, like any kind of model would not arrive there by simply combining pet and fish. Is that the underlying problem? I'm not sure, because I mean, if you learn about pet dog, if you learn about pet bird, if you learn about pet lizard, there is some form of commonality between these things, right?
Absolutely. Yeah, you can take the word pet and you can attach it to a bunch of things that we know, and then eventually it can stick to any of them. But what's going on? Do you really think it's just an associative maelstrom going on inside?
No, not an associative maelstrom, but picking up a structure that exists in the world. I think that's what's happening.
Your structures were prototypes. Now you don't see prototype dogs. You see all kinds of different dogs and cats and animals. And the prototype is something weird that comes out of this kind of processing. And then when the prototype is like the smoke too. It's something that if you look at a lot of animals over and over again and you do kind of a morphing of them, you get something that's the average of all of them. But that's not what we're talking about when we're talking about what an animal is, a pet is, etc. We're talking about pets and fish, and we know what fish are. We know what pets are because we know what pet means and what fish means.
But I mean, for this problem to work, you would need to ask a person who doesn't know what a pet fish is, right? And this person would come up with some kind of estimate what a pet fish is by combining these things. It's just by learning what a pet fish actually is that you get a different kind of representation for it, because the word exists already. And then to know what a pet fish is, you need to make this experience with a pet fish.
Yeah, what I hear when you say that is that if you tell somebody who never heard of people having goldfishes as pets, etc., but who simply hears what is a pet fish, right? What they'll do is combine stuff that they already know in some way, but I don't think it's associations like what you're saying. It's not what appeared in the context of the word pet, what appeared in the context of the word fish, where did the two appear together, and we come out, and that's your giraffe with a
I mean, at this, why not? Because if you then ask the person, okay, now use the word pet fish in sentences. I mean, what you get from this distributional addition or from this image-based addition is essentially an estimation of how you could use this word and how this word would be probably distributed in language.
Which is exactly what GPT-3 does. But I hope you don't say that GPT-3 understands meaning or understands words.
I'm actually not familiar with the model.
GPT-3 is a glorified LSA that's very much in the news for the last 3 or 4 weeks because it produces such coherent text and it can be directed to particular topics and it makes sense, and it's what you can have a conversation with Mozart about sonatas, etc.
Okay, but then we're just running into the philosophical zombie model problem again, right? Because then it's just, okay, if the thing can act like a human, does it understand the thing or not?
I don't think so, because with the GPT-3, everybody knows that it doesn't understand anything, that this is just a trick that comes out of correlations and frequencies. They're scared of it because it can be used in terrible ways, but they don't think that you have something passing a Turing test there. It's just using the distributional properties of words and conjunction properties to produce coherent, some more words. But it's not a model of what's going on in our heads.
But what if if it passes the Turing test, what then? I mean, at this point, you could consider this to be a technical limitation of the model, right?
I don't think so. But anyway, I think that there are 2 Turing tests, and Arthur, one of them is the verbal only one, and then the other one is the sensorimotor one. And there's no way on earth that GPT-3 or LSA could pass the sensorimotor one because there's no motor part. You're not doing anything. All you're doing is associating stuff.
No, but that's essentially what I mean. That's why I'm doing this whole kind of research, because of course language is one form of experience we make with the world, but it's definitely not the only form of experience we make with the world. I do believe that if you had a way of actually completely coding every piece of experience we make and running them through a system that is like our brain, we would get to some state where we would have an automated system that could pass both Turing tests.
I'm not sure what you're imagining, but I mean, forget about the Turing test can be applied to any organism, not just humans, okay? In principle, we could ask for a Turing test for a monkey. They don't have language. So all they have is sensory motor experience.
But they have
do you think what they're doing is looking at still photographs in context and counting them,
no.
In the end producing a connection?
No, definitely not.
Do you think that they're averaging the still photographs and doing it with prototypes?
What I do think is happening is that they make visual experience and recognize when they make experience again with the same thing. And I mean, this vision model is just a very stupid approximation of this thing. Like, okay, this is a dog, this is a dog. And once you have the possibility to make repeated experience with the same thing, then you can form a representation of the thing.
Well, last week's talk was about that. It's about how you learn to categorize things. And we know but that doesn't involve any of the things that you were talking about. It involves supervised learning on inputs where you get with correction as to that's a dog, no, that's a cat. Until finally your brain is doing something when it's saying that's a dog and that's a cat, and it's petting the dog and it's running away from the lion. It's doing something, and your brain learns, and it doesn't have to be a linguistic brain, to do the right thing with the right kind of thing. You're learning what kinds of things there are, sensory motor learning, and then you're learning to do things with them.
But that's exactly what our vision models do.
But I don't think your visual model is doing that at all, because your visual model isn't really doing.
The vision model just tells you whether this picture is the same thing as this picture. The vision model doesn't run on language at all. It's completely language agnostic. These labels are just a nominal scaled variable telling you what is the same thing and which are different things. You could call these things 1, 2, 3, 4, 5, and it would still work.
Yeah, and if it does it without feedback, then it's doing ordinary unsupervised learning. But if it's getting feedback, you're right or you're wrong, then it's doing supervised learning on matching things.
It's doing supervised learning, I think, if I'm correct. It tries to predict what's on the image, and then it gets told whether that's correct or not.
Okay, let me leave it at that. I don't agree, but let me leave it. I have three more hard questions. One of them is, what's the difference? We've talked about pet fish. What's the difference between red apple and apple red? And by that, I don't mean a giraffe pimp and pimp giraffe. I mean, red apple is really just a composite name for things that are apple and red. And so you call them red apples. Whereas apple red, in a language that doesn't, like Russian, that doesn't have a separate word for predication, it's just saying the apple is red. Okay, so what's the difference in how does your approach to handling composition handle the difference between just literally a compound name and a proposition which says apples are red? Apples have the property of being red.
So it's about truth conditions, essentially, that one thing has a truth condition and the other does not?
Well, yes, only propositions have truth conditions, that's for sure. But there's okay, but from the point of view of your model, they're just words. So you have X, Y, and YX. YX is as a proposition, XY is just a compound name.
Yeah, that's because it's, I mean, our model is really just designed to be a model of meaning combination in the sense of merging two things, like compounding, essentially.
So
it's not designed to be a syntactically informed model that can handle truth conditions. I think I've seen that Stephen Clark is on your distribution mail list. I think he could make more informed statements about those kind of things.
Okay. So
because really we are just concerned with, we are not concerned with statements. We are just really concerned about combinations of two things.
Yeah, compound descriptive. Next question. We already asked about what about the motor, and Art said it's invariants that we're talking about, and invariants are sensory motor features. They're basically features that are determined by the shape of the object and the shape of the subject, if you like. Right? How is that sense of affordances as features? How is that to be incorporated in something that sees features as sort of passive properties? You know, some things are red, green, brown, etc., etc. It's not something I do with my body that I can do with that kind of thing and I can't do with that kind of thing.
So the question is, does the model capture that, or could it be?
Can the model handle sensory motor affordances?
I'm pretty sure that this model, no, because it doesn't interact. It just classifies. So I'm pretty sure that this kind of vision model that we are using does not handle these cases. I think to get to something like this, you would need something that actually starts interacting with the world. And I mean, there you have these, I'm missing the word, these robotic studies where we actually have agents that start interacting with the world and then communicating with each other, like this work by Steels and Sprangler and colleagues. And I think to get to something like this, where you encode interaction with the world, you need interaction with the world, at least on a simulated basis. And with a model that just learns to classify two things into being the same or different, I mean, maybe the information is somewhere in there, but I don't think it is.
Art?
Are you asking me to answer that question or other question?
Declare yourself on this.
If you have to turn on the light.
Yeah, no, I agree with Fritz in that regard. It seems to me like at this stage, these sorts of models just can't do it because they can't interact with the world. And I also agree with Fritz that one way of thinking about how to get there may be in terms of robotics. and at least developing semantics for this robot. It may not be the same semantics that we have because the robot's body will be different, but it may give us a way of thinking about what we mean by meaning once we get interaction in there. And as long as I have the floor, I just wanted to go a little bit further and to go back to Fritz's questions at the end of his talk about, you know, are these just fancy tools or are they helping us along? And I think the answer is, you know, that it's both. That certainly it is a fancy tool, and I'm sure it can be used in a technological sense, you know, to, you know, help internet search or whatever. But it's through discussions like this that it also helps us along as psychologists, because we get to essentially compare your ideas to other hypotheses, you know, and by listening to you, it really helps us formulate our questions better, so that we can make advances. You know, we can look at your work as a model of human cognition and then, you know, propose another model and propose experiments to try to decide between them. And so, yeah, to the extent that you're providing a very sophisticated analysis, but as Stephen points out, it's really just sort of associations, you know, we don't have propositions yet, we don't have truth value and so on and so forth. Yeah, it then allows us to think through what's important for human cognition. So yeah, I mean, I think it's clearly an advance in that regard by, yeah, helping us think more clearly.
I agree, and I remember this is Montreal.
Yeah, maybe a comment on.
Yeah. Go ahead, Fritz.
Maybe to put a comment on this. I mean, I think you often see these models portrayed as depending purely on association, because that's what they're giving you. They're giving you some kind of similarity score between two things, and most people look at these similarity scores. But the models are not just these similarity scores. It's not just mutual similarities. You actually have dimensions with values. And these things up to date are, I mean, they are a big black box. We don't know what these things actually encode, what these numbers mean that make up these vectors. And I think that this is something that we should harvest more. Like there is more content than just an association to another thing. There's a list of several hundred numbers encoding something. And I think finding out what these 700 numbers encode would be extremely interesting. For example, I recently ran a quick analysis on this sensorimotor rating norms, and these are extremely well predicted by these purely language-based vectors. So I can predict the pattern of these sensorimotor norms from these vectors, which doesn't mean a lot, but it tells you at least that there is some content in these things. And I think to really understand what's happening there and to make a progress there, it's not just about looking at relations between things, but looking at the thing itself. Although I don't really know what exactly to do there, but I think there's a lot of information that we are not using currently with these things.
Okay, go ahead.
Yeah, there's a question.
Fritz, at the beginning of the presentation, I saw concept learning. I was very excited about the title because this is the subject of my thesis. But excuse me, for me, I expected at the end to have vectors that represent concepts. I didn't see concept learning. It was just vectors that represent words, and words are signs, image, our science, and it's very dense concepts. So I didn't see any concept learning. So
yes, depending. Yes, I think once you apply a slightly more sophisticated definition of what a concept is, yes, yeah. I mean, maybe we can start from this definition. So what would you have needed or expected?
Je vais utiliser un dit sémiologique, je ne les connais pas en anglais. So, un concept, il signifie. Okay, in English, I don't know how to say signifie. It's something that we don't find in the real world.
Yes.
And la position intermédiaire entre le mot, l'image, c'est le concept, c'est la représentation qu'on a. Une image, c'est pas un concept.
Maybe I get it, and maybe I can try to answer. So, the way I see these things, it's not. I mean, it's a word, and it's not a picture. It's something that is learned from words and pictures.
What is the formalism of this thing? Is it an ontology? Is it a vector?
It's a vector.
It should be something.
I mean, in my case, it's a vector. I don't say it is a vector, but sorry.
Maybe I didn't understand the relationship between the network that deals with the text and the network that deals with the pictures, because I didn't see how you emerge the vectors that represent the concepts.
Yeah, I think the next step in this thing would be something that integrates these different ways, these different types of information, because right now they stand next to one another. So there's some representation, like a list of numbers representing the word meaning, hopefully, some list of numbers representing what the thing has learned from pictures, and they are not integrated into one thing yet. I mean, if you want to go super stupid, you could just concatenate them. That would be, of course, you would then have to care about dimensions and how many of each contribute to something, but that would be like the super brute force approach of combining them. And
yes, I asked whether this is arithmetic operation or concatenation, because in my opinion, I prefer to perform concatenation because it's more representative. When you make arithmetic addition of vectors, 5, for example, the number 5 can be 4 plus 1, and it could be also 3 plus 2, and 3 plus 2 doesn't mean 4 plus 1.
Yes.
It's just the remark.
Yeah, that question was in relation to the compounds. There we need something that has the same dimensionality as the rest.
Okay.
You wouldn't, because we don't want to assume that combined meanings suddenly start populating a different semantic space than regular meanings.
Okay.
That was the reason for that. I think concatenation is one way to go. The technical problem with concatenation is that, I mean, if you want to then, for example, compute similarity scores, and you have 400 visual dimensions and 300 language-based dimensions, suddenly the visual dimensions start counting more just because there are more dimensions. And I think simply concatenating is too easy there. At least you have to apply some form of dimensionality reduction on top of that, maybe something more informed even. That would be my idea.
In all cases, in the word embedded, the most known approaches like word2vec or Glove or FastText for Facebook, they use concatenation even for another approach rather than concatenation.
I'm turning brighter and brighter because it's getting dark outside. I I can still see me.
Yes, thank you very much. I have to go and see you next week.
Thank
you. Fritz, let me thank you on behalf of everybody.
Yes.
These are the most loyal citizens that are still here, but it was a wonderful 2.5 hours. And I want to thank you very much for coming to Montreal virtually.
Thanks a lot for inviting me. It's really great.
Bye-bye, everybody.
Okay. And